Hey, Physics 112 students, Chris McGrath here again, at this time to give you some solutions to the problems that I gave you in class on Thursday morning, the 31st day of January. I enjoyed very much being with you all in the class there, and I hope that you enjoyed that presentation of the material in the flipped classroom style. And to complete that cycle, I do like to make solution videos that go with problems that I give in class so that you're not left without those solutions. So that's what this is. Just a quick word about how to use the solutions video. Similar to the notes video, you can pause anytime if there's a problem that you're not sure, you got to a certain point, you kind of got stuck. If you get unstuck, you should pause the video, try to finish it yourself, and of course you should try to do them all to the very best of your ability before you watch this video. So thanks again for letting me be part of your class, and let's go ahead through the solutions here. I'm going to just, for number one here, I'm going to write down some things that we know and just talk about them briefly. So electric force between two charged particles is equal to this. This is Coulomb's law. And I think it's worth saying that electric force is equal to this in the particular case where we have 2-point charges. And there are other situations where you might have a charge distribution. These are some of the things you looked at in chapter 16, where there might be electric force as a result of lots of charges, or maybe a wire or a sheet that's charged or something like that. So this is just for 2-point charges, and all of those other things typically involve integrating some version of this with lots of charges that are distributed around. So I'm saying that because I think it's real important to understand when we can use these particular models. So this is for 2-point charges, and lots of other things that you got in chapter 16 were a result of applying this in different situations. Of course, that's a force that's measured in newtons. The electric field is how much force you would have per unit of charge, and that's newtons per coulomb. So, I mean, it might happen that you just have one charge, in which case the electric field looks like those lines radiating outward, and as you get further away, the electric field, those lines would get smaller. They're pointing away because we imagine that that's how much force there would be if there was a positive test charge there. So the units would be newtons per coulomb. And of course, you don't just have electric fields around point charges. They could be more complicated charge distributions, and might apply Gauss's law or do some of the other things that you learned about in chapter 16. So the next thing, I think probably if there was a most important thing from the sections 17.1 to 17.3, where I was responsible for your notes there, I think probably the most important equation would be, new equation, would be this one. That the potential difference is equal to the opposite of the integral from an initial to final position through that electric field with respect to position. And lots of things come from this. Just like in chapter 16, what we end up with here depends on the electric field, and the electric field depends on the distribution of charge on what's going on. So this can take different forms. And if you choose ground where V equals 0, then you can define the potential difference at some position. That depends on choosing that ground. Otherwise, you can talk about the delta V. And then we know that the potential energy, electrical type, is the charge times that potential, electric potential. I want to point out the similarity between these things. So electric potential is potential energy over charge, just like electric field is force over charge. So the units here would be joules per coulomb. I don't want to say unfortunately, but we do get a unit for this, the volt. It's maybe just a tiny bit unfortunate because it does obscure what's going on here, that when we're talking about electric potential, we're talking about how much potential energy we would have per unit charge for some positive test charge. And that's in joules per coulomb, or in other words, volts. All right, moving on. So in number 2, we had 2 plates with uniform charge density. You should put that plus in front of there, sorry. And that means that we're going to have a uniform electric field between those plates. And they were 10 centimeters, or 1/10 of a meter apart. So in part A, we just looked for a relationship back from chapter 16, that the electric field is equal to that charge density divided by epsilon sub 0. And when you do that, you should get, I'll spare you the math, you have your, I hope that you have nearby to you this solution, all these written out. You might be wondering, why am I bothering making this video if you already have this? I think my students generally find that it's nice to have somebody kind of go through it. It's a little bit more than just the static document like this. So it all depends on how much it made sense to you, I suppose. So anyway, if you could refer to that, you can see those equations with the numbers plugged in. I'm just going to go ahead and cut to the answers in those situations. And what's the direction of the electric field? It points from the positive away from positive to negative. So that would be up. And also that's all for part. I thought maybe there was another part to that A, but no, there is not. So what's the electric potential at a point halfway between the plates? So this is for the first time we're going to introduce this. And my electric field, I'm not going to put a vector hat on that because this is just one-dimensional. It's always the same everywhere. So we'll take the R direction here to be that only direction we're interested in, up. And this becomes a very easy integral in this case because the electric field is constant. So however you think about your integrals, if you think about the area under this curve, this is just a horizontal line here. And my initial, we go from 0 to 0.05 meters. I'm choosing to go from 0, not because I love the number 0 so much, but because this is a ground. That's where we know that the electric potential is 0. So that means that since this is ground, then the value of this integral will be the value of the electric potential at that point halfway in between the two plates. So that means the value of this integral is, I think it's negative 28.3 volts, and that is the electric potential at that location halfway between, because this is ground. Right? This is the potential difference between here and here, but since it is a 0 here, then it actually is negative 28.3 volts there. All right. Oh, and there was another part to this one. So does this value V increase, decrease, or remain the constant if the point is closer to the negatively charged plate? So if we go closer here, we were at 0 electric potential here, and then we were at negative 28.3. So when we get to here, it's just we're just going to keep multiplying by how far away we are. It's going to continue to be a simple integral like this. So here it would be about 56.5 negative. So it's going to decrease there. And why 56.5? It's just double that. It's twice as far away as that midpoint. And we're going to use that number in a minute anyway, in this part C. So if a proton is released at the positively charged plate, what will its velocity be when it reaches the other plate? And we're going to take an energy approach. Mechanical energy is conserved here, so at the release, the potential energy of the proton here is going to be 0 because that's where we chose our ground. If V is equal to 0, well then so is potential energy, right? These are, right? If V is equal to 0, so is potential energy and vice versa. So we got 0 electric potential energy at that plate, and we're releasing it from rest, so it also has 0 kinetic energy. So how about at the negatively charged plate when it gets there? Well, the electric potential energy is equal to the charge times the electric potential there, and the kinetic energy is equal to 1/2 mv squared, just like kinetic energy always is. And let's see what we can do here. So total energy before, total energy after are going to be the same. So we have 0 total here, and here I've got the charge of a proton, positive elementary charge, and the potential here we figured out, that's negative 56.5. We get that exactly the same way that we did part B, just going from 0 to 0.1 meters. And that's my, if you think about this being joules per coulomb, the coulombs cancel out and we get joules, which is what we're looking for. So that's good news. And then plus 1/2, the mass of the proton is 1.67 times 10 to the negative 27 kilograms times that velocity we're looking for squared. So you can figure that all out and solve for that velocity. Should get 1.04 times 10 to the negative, times 10 to the 5th meters per second. Pretty quick. All right. In part D, because the electric field is constant, that means that the electric force on our proton is constant, and that means that acceleration is constant. And if the acceleration is constant, then you can use kinematics equations to do this. So I just wanted to run through that. It's always fun to do a physics problem more than one way and get the same right answer, right? Good time. So here's how we're going to do that. Need to find that electric force. So that's my elementary charge times the electric field. So the force on that proton is 9.04 times 10 to the negative 17th newtons. And since this is the only force, we're ignoring the tiny negligible gravitation. That's not going to figure in here. So our acceleration is just this electric force divided by the mass, just a rearrangement of Newton's second law there. So our acceleration is equal to this force divided by the mass of the proton, and that comes out to be 5.41 times 10 to the 10th meters per second squared. And once we have that, since we're looking for the final velocity, I'm going to dust off this old kinematics equation. I don't know when the last time is that you saw this, maybe recently, and use that here. So my final velocity squared, this is 0, my initial velocity, plus 2 times the acceleration that we found here, times the displacement that proton's moving through. And if we solve for VF there, we get 1.04 times 10 to the 5th meters per second. Good news. All right, so that's how you do it the kinematics way. Number 3. Got a charge nailed down to the origin of an XY axis, like so, and that charge has a magnitude of 3.25 microcoulombs positive. And we want to find what is the electric potential at the location right here, 0.25 meters in the positive I direction or out along the x-axis. What is the electric potential there? We're not putting a charge there, we're just investigating what's the electric potential at that location. Okay, so how do we do that? Well, if you look back at your notes, if you want, this is the little bit of calculus that we did that gives us the electric potential in the vicinity of a point charge. This is a good point to reflect on when we can and cannot use particular equations that we have in our bag. This applies to in the vicinity of point charge. That's when we can use this. Looking for electric potential around a point charge, and that's exactly what we're doing here. This is just the distance from the point charge. It doesn't matter in what direction. If we drew a circle of radius 0.25 meters, the electric potential would be the same at all those locations. Let's go ahead and calculate that. So the electric potential this far away from our point charge is equal to our constant times 3.25 microcoulombs over 0.25 meters. And that's equal to 1.17 times 10 to the 5th volts. That was part A. Part B, we are going to find the potential difference which is the electric potential between two different points, between these two. So that is, well, we already found this, didn't we? That's right here, our answer for part A. And so I think we just need to find this. And the process for finding that is exactly the same as it was for finding this. So to do this here, we just need to 1 over 4 pi epsilon naught times the same charge, 3.25 microcoulombs, and 0.35 meters here, minus, we already did this, you can put that back there if you want, but we already know now that that's 1.17 times 10 to the 5th volts, and if you do some math there, you should find that that's negative 3.35 times 10 to the 5th volts. That's from here to here. If you're wondering, like, what does it mean? Like, what does this really mean? Like, what does it mean that this is negative? Remember that these volts are joules per coulomb. This is how much potential energy a positive test charge would have if it was at some location. So let's just think about for a second. If you put a charge here, a positive test charge, then it would have the potential energy that it would have. It would want to be repelled. Well, it would be repelled from this positive charge here. So if we were holding it down there, it would be holding it down, and if we let it go, it would want to release off in this direction. Now here, if we had our positive test charge here, it would also want to repel, but it wouldn't want to repel as enthusiastically, let's say. Sorry about that, I was off the page. So this one would want to repel off this way, and this test charge, if we put one here, it would want to repel off this way. This is negative because we're going from a place where there's pretty strong repelling to a place where there is less repelling. So there is less potential energy here. So as we go from here to here, we're losing potential energy per coulomb. It's becoming less. So I don't know if that helps a little bit understand maybe intuitively what's going on there, but that's what's going on there. In part C, we're interested in doing a little energy stuff. Again, we're going to release a, let's just call this the 0.35 right here, and we're going to release it from here. So like we were just talking about, it's going to be repelled up this way, and we're interested in how fast then will it be going when it has gone half a meter, so from 0.35 up to 0.85. From 0.35 up to 0.85. How fast will it be going there? All right, so let's set up that energy problem. So at the release, we've got potential energy that's equal to charge times electric potential. And I'll call this, at the release, we're releasing it at 0.35. So, well, we'll just pull that out from here. And the kinetic energy, since this is at the release, there's going to be 0 kinetic energy. And when it gets to 0.85 meters up there on the y-axis, then it's going to have some potential energy. Right? It will have, you could think about, per our discussion there, we'll have more or less. Think about that if you want. Maybe pause for a sec. And the kinetic energy is going to be equal to 1/2 mv squared. And we'll try to find that v. So there are no non-conservative forces, so that means my energy is conserved. So QV at the 0.35 meters is equal to QV at the 0.85 meters plus 1/2 mv squared. And you've got all the work on that sheet that I gave you, what that all looks like when you put everything in. And you should get, after all the number crunching, about 4.43 meters per second. And part D, how come we can't use that kinematics approach that we used in part D for number 2? And the answer is these kinematics equations only apply if acceleration is constant. And our acceleration is not constant here because the force is, since we just have one point charge here, another point charge here, Coulomb's law would apply, so that means our force is an inverse square law, and it's decreasing with the inverse square of the separation of those two charges. So we do not have constant force or constant acceleration there. All right, number 4. Where's my number 4? Around here somewhere. So in this problem, we've got another xy coordinate plane, and got three charges, Q1, Q2, and Q3. And we're, let's see there, what are their charges? This is 2 microcoulombs. This one is negative 1.5 microcoulombs, and this one is negative 1 microcoulomb. Okay, so in the first part, we're interested in finding the total electric potential at this location right here, the unoccupied corner of that square. So let's call this position A. So what is the total electric potential at that position A? Well, that's V1 plus V2 plus V3. This is at the very end of your notes. The electric potential, because of a cluster of point charges, in this case 3 of them, we just find the electric potential due to each one and add them up. So when we do that, you can factor out your constant, and we get this Q1 over R1 plus Q2 over R2 plus Q3 over R3. And like in the notes, I just want to emphasize what these R's are. So this is the location we're interested in. So the R1 is the distance from that location to Q1. Likewise, this is R2, and this is R3. And R1 is just going to be just a little Pythagorean theorem here. This is about 0.14, and these are just obviously 0.1 meters. So you can refer to the sheet that I gave you with solutions if you need to, and that comes out to be that. In part B, we want to find the potential difference between this point to a point that is 1/10 of a meter up higher than that. I'm going to call this point B. So we also need to find that potential difference, we need to do the potential difference here due to those charges, and do that just like we did in A, and then subtract what we got here. So setting that up just like I did here, I'm going to go ahead and write that out just so we can make sure we get the R's right. So it's 1 over 4 pi epsilon sub 0, and we'll have Q1 over R1 now is going to be the distance from here to this. So a little bit of Pythagorean theorem there should get you 0.22 meters. And then Q2 from this new location is that diagonal across that square. That was that 0.14 that we saw there, plus Q3 over, well, that's a straight up 0.2 of a meter there, and then minus the answer we got from part A. Minus that right there. So that should give you 3.68 times 10 to the 4th volts there. And last part, in part C, question is how much work would it take to get a charge of positive 1.25 microcoulombs from here to here? How much work would we have to do to get it from here to here? Well, the work done by the conservative force, by the electric force, is equal to the opposite of the change in potential energy. Remember, we talked about this in the notes with the box that you were moving up. That box of mass m, if we move that up to here, the change in its potential energy is equal to mgh but the work done by gravity, since gravity is the other way, is negative mgh, so that's just that relationship there. Now, we're not talking about the work done by the electric force, though. We want to know how much work is done by us, or whatever force is going to get it from here to here. How much work would be done by us, and that's just the positive change in potential energy. So let's see, how do we get that? Well, since the potential energy, electric potential energy, is charge times potential difference, or sorry, electric potential, then change in potential energy is equal to charge times potential difference. And we've got the potential difference from here to here in the problem right there in part C, or part B rather. So the change in potential energy, which is the work that we're interested in, and that's just equal to Q, our charge, which was what, 1.25 microcoulombs, times the potential difference, 3.68 times 10 to the fourth. That's volts, but that's the same as joules per coulomb, right? So you can see there that we are going to get units of joules, and that's about 4.6 times 10 to the negative second joules. I hope you found that helpful, and I hope you enjoyed the overall little flipped classroom demo there. It's always hard to drop in and do your thing in a different context with different students, but I thought you all made a great job of it in class on Thursday, and I did enjoy meeting you all and working with you in that context. And I hope this video helps you sort of see the complete picture of what I like to do with my students, and put in a good word for me. Thank you very much. Enjoyed meeting you all, and hope to see you again sometime.